Welcome to this session. Today we are going to discuss second order homogeneous recurrence relations. Before starting this, one more problem is there in first order recurrence relation. So after completing this problem, then we'll move towards the second order recurrence relation. So here, this problem we are going to consider. So there are three pegs will be there, fixed vertically on table, and n circular discs having holes at their centers and having increased diameters are slipped on one of the pegs, which is the largest at the bottom. The largest circular disc is at the bottom. Then the discs are to be transferred one at a time, one another peg, with the condition that no time a larger disc is put on the smaller disc. So larger disc will not keep on the smaller disc. Determine the number of moves for the transfer of all n discs so that at the end of the disc are in the circular and original order. So let us consider there are three pegs will be there. Let us just we are taking which are fixed here. Three pegs are there. And here, now the thing is, there are n circular discs will be there. N circular discs. Okay. Let us, we are just taking, this is larger circular discs, and let us, we are taking this as a larger one. And next, before that, next larger is this, next larger is this, and next larger is this. Like this, it is going to be arranged. So there are n numbers will be there. Now the thing is, we have to transfer these circular discs in any one to the one of the peg, so that it should be in the same manner the circular discs are going to be arranged. So for that, there are n circular discs are there. So now n minus 1, see letters an moves are required. An moves are required to transfer n discs. An moves are required to transfer n circular discs. So let us consider there are an moves. An is the number of moves required to transfer n circular discs. Initially, A naught is equals to 0. Initially, A naught is equals to 0. Now the thing is, n minus 1 circular discs are, we are going to move to the one of the peg in the opposite order. In this opposite order, we are going to arrange. So here n minus 1 circular discs are only we are going to keep. So if I am going to remove n circular discs, so there is n minus 1 moves will be there. N minus, let us say I am just taking a number of required n circular discs. So let us say, then let us, I am just taking n minus 1 circular discs are we are going to keep on one of the peg 2. Let us say this is a peg 1 and this is a peg 2 and this is peg 3. Now the thing is, I am going to transfer this, the larger circular discs here, and the remaining I am going to replace, I am going to move in the another peg 3. So in the same order, whatever we are going to remove from this peg, in the same order we are going to arrange. So here, n minus 1 moves are, we are moving in 2 times, and we are going to take another one is a larger circular disc. It is going to move 1 time. So the total number of moves are an is equals to 2an minus 1 and plus 1 and plus 1. So this is just n minus 1 circular discs are moving twice, so that we are taking it as a 2, and larger discs we are going to move only one time. Then if I am going to substitute n is equals to n plus 1, then the recurrence relation will become an plus 1 is equals to 2an plus 1. So this is the recurrence relation for this scenario. So here there are n circular discs are arranged in a peg 1. So which the diameter is goes on reducing whenever it reaches to the top. Then we are just moving the n minus 1 circular discs onto this another peg P2, and then larger circular discs we are going to move to P3. So n minus 1 we are going to move to peg 2, and next another n minus 2 we are going to reverse order, we are going to move to peg 3. So subsequently whatever the peg 3 will be having in the same order, whatever the original peg it is having in this order, we are going to get this. So for that we are taking, there are 2 times of n minus 1 disc, and then one is the larger movement. So we are going to consider the recurrence relation is like this. Now to solve this recurrence relation, now we are going to find the nth term at the end of the original, determine the number of moves transferred. If n is unknown, now we are going to verify if n is equals to 5, what is the number of movements, and n is equals to 10, what is the number of movements, n is equals to 15, what is the number of movements. For that we are going to solve this recurrence relation. So for solving the recurrence relation, this is nothing but a non-homogeneous recurrence relation, because f of n is not equal to 0. So here it is of the form an plus 1 is equals to can plus f of n. So the solution is an is equals to c to the power of n, which is nothing but 2 to the power of n a naught plus summation and 2 to the power of, this is c to the power of n minus k and f of k. F of k is equals to 1. F of k is equals to 1. So n is equals to 1 to k, or k is equals to 1 to n. K is equals to 1 to n. Let us, I am just taking k is equals to 1 to n. Now I am just taking, initially there is no movement, a naught is equals to 0, subsequently this will become 0. Then I am going to take this as summation of 2 power n minus k, and k is equals to 1 to n. So if I am going to substitute here, this will become 2 power n minus 1 plus 2 power n minus 2 plus 2 power n minus 3 and so on, 2 power n minus 1 plus 2 power n minus n. Subsequently this is 2 power n minus 1 plus 2 power n minus 2 plus and so on. This is 2 power 1 plus 2. 2 power 0 is 1. Now let us, this is in geometric progression with the common ratio is 2. So then this we are going to solve it. The sum is nothing but a to the r to the power of n minus 1 by r minus 1. So the common ratio is 2 and 2 to the power of n. There are n terms will be there. R to the power of n minus 1 by r minus 1. Here r is equals to 2. So this is nothing but 2 to the power of n minus 1. So because this is 1, so subsequently what we are going to get, the solution is an is equals to 2 to the power of n minus 1. This is the nth term, or else the solution for the given recurrence relation. So non-homogeneous recurrence relation. Suppose if I am going to take n is equals to 5, how many number of moves? Just we are going to take it as n is equals to 5. So here 5 is equals to 2 to the power of 5 minus 1. Whatever the value we are going to get, those many number of moves are required to transfer from one peg to another peg, which is arranged in the same order or in the specified whatever the mentioned in the given problem itself. Suppose if I am taking n is equals to 2, then a2 is equals to 2 power 2 minus 1. There are 3 moves are required. 3 moves are required. If 2 pegs will be there, So then that is going to be considered, and next like that we are going to substitute, and this is known as a solution of the this problem. This is nothing but which is also known as a towers of Hanoi problem. So this is one of the problem which is related to the first order recurrence relation. Now let us concentrate the second order homogeneous recurrence relation. So any recurrence relation which is of this form, Cn an plus Cn minus 1 an minus 1 plus Cn minus 2 an minus 2 is equals to 0. Here Cn minus 1, Cn minus 2 all are constants, real constants, with the condition Cn is not equals to 0. Then this type of recurrence relation is known as second order linear and homogeneous. Why homogeneous? There is no function. Right side it will be 0, or f of n is equals to 0. So we are calling it as a homogeneous. So second order homogeneous recurrence relation with constant coefficients. So we are going to generalize this. See, if I am going to consider the third order recurrence relation, homogeneous. So Cn an plus Cn minus 1 an minus 1 plus Cn minus 2 an minus 2 plus Cn minus 3 an minus 3 is equals to 0. That is nothing but a third order homogeneous recurrence relation. So now we are going to find out the solution for this recurrence relation. So we are going to find the solution for this. So for that, let us assume that we are taking a solution which is of this form. We are going to take it as an is equals to c power n, c into k to the power of n, be the solution to the equation 1. Here c is not equals to 0. Then I am going to, whenever if I am saying that this is the solution, then this satisfies this equation. So here Cn and next c k to the power of n. The first I am just substituting. Now Cn minus 1 and an minus 1 is nothing but c k to the power of n minus 1 plus Cn minus 2 c k to the power of n minus 2, which is equals to 0. I just substituted because it is the solution. It is the solution for the equation 1. Now let us, I am going to do k square into c. I just took common, or else first k square I am just taking. Then this will become c and cn. Then k to the power of n minus 2 we took. K to the power of n minus 2 I am just taking common. So then this is k square plus cn minus 1, and then I am going to take it as k, and this is cn c, which is equals to 0. Now this is, I am going to write it as then c, and this is the whole thing will become 0 because this is not equals to 0. So I just took c also common from this. So then cn k square plus cn minus 1 k plus cn is equals to 0. Here c is not equals to 0. And so I can say that cn k square plus cn minus 1 k plus cn minus 2 is n minus 1, then it is n minus 2 is equals to 0. So this should be equal to 0 because the product is 0, because c is not equals to 0, then ultimately this should be equals to 0. So this is known as the auxiliary equation. This is known as the auxiliary equation. Let us call this as a equation 2. So now if I am going to take an is equals to c k to the power of n be a solution, so it must satisfy the given equation. So the given equation 1 is reduced to equation 2. Now equation 2 is called the auxiliary equation or characteristic equation of equation 1. Now we are going to find out the roots of this. So the roots, if I am going to find out, then there are three possible cases are going to be arise. So one is the roots are real and distinct. The roots are real and distinct. Then the roots are real and repeated. And here the roots are complex roots. So these are the three cases are going to be exist. Then we are going to discuss one after the other. So first case 1. Let us the roots of this auxiliary equation are real and distinct. So those roots are, let us assume that it has k1 and k2. So now, whenever the roots are real and distinct, then the solution which is of this form, an is equals to a k1 power n plus b k2 power n. Here a and b are arbitrary real constants. Whenever the roots, if you are going to find out the auxiliary equation, the roots are real and distinct, then this is the solution. Now the second one, if the roots are repeated roots, so k1 is repeated twice or k2 is repeated twice. So the repeated root, if I am taking it as k, whatever it is, k1 is repeated or k2 is repeated, then whatever the repeated root, then I am just taking it as k, then the solution, it is nothing but this is the solution. This is the solution for that. So this is the solution for the whenever roots are repeated roots. Now the roots are complex roots. Whenever complex roots will be there, they are conjugates of each other. Suppose if I am taking k1 is equals to p plus iq, then k2 is equals to p minus iq. K2 is also p minus iq. Then we are going to consider an is equals to the solution as r power n, a cos n theta plus b sin n theta, where a and b are arbitrary constants and r value is nothing but the modulus of k1 or modulus of k2, which is equals to square root of p square plus q square. P is nothing but the real part and q is nothing but the imaginary part of the root. And here theta is equals to r we are finding, and then theta is equals to tan inverse of q by p. Tan inverse of imaginary part by real part. So from this we can calculate what is r and what is theta. Then if you are going to substitute r and theta in this expression, subsequently we are going to get a solution for that. This is nothing but the general solution. A general solution to the recurrence relation. Now, let us, we are going to solve some of the problems which are related to the second order homogeneous recurrence relation. Now, see here, I am just taking a recurrence relation is given like this. N is greater than or equals to 2. And then the conditions are given, A0 will be there, A1 will be there. Now we are going to find the solution for this one. So here, what is the solution for this is, just, it is not correct. So whenever, if I am going to consider the solution for this is, just we are going to take the auxiliary equation for the given equation. So what is the auxiliary equation? See here, the auxiliary equation is Cn k square plus Cn minus 1k. So what is the auxiliary equation is Cn k square and plus Cn minus 1k plus Cn minus 2 equals to 0. So this is not required, it's wrongly typed here. Now, so for this equation, the auxiliary equation is this. What is Cn is the coefficient of An. Cn is the coefficient of An, which is equals to 1. What is Cn minus 1? It is coefficient of An minus 1. It is 1. What is Cn minus 2? It is coefficient of An minus 2. It is minus 6. So just substitute this. 1 into k square and next 1 into k minus 6 equals to 0. So which is k square plus k minus 6 is equals to 0. So then this is k square plus 3k minus 2k minus 6 is equals to 0. So k into this will become k plus 3 minus 2 into k plus 3 equals to 0. So it is k minus 2 into k plus 3 equals to 0. So k equals to 2 and k equals to minus 3. So these two roots are real and distinct. Then what is the solution for this? An is equals to what is the solution for this? Say A k1 to the power of n plus b k2 to the power of n. A k1, let us say I am just taking 2 to the power of n plus b I am going to consider then minus 3 to the power of n. So this is the general solution. This is the general solution for that. Now, whenever the general solution is given and there are particular conditions are given. Particular conditions are given here. So with this we are going to calculate what are the values of A and B. After that we are going to substitute in this. Then we are going to get a particular solution for that. So if I am going to take it as n is equals to 1, n is equals to 0, then I am going to get A naught is equals to A 2 to the power of 0 is 1 and the next plus B 3 to the power of 0 is 1. Subsequently, what is A naught is equals to minus 1. So A plus B is equals to minus 1. Next, another one is n is equals to 1. Another condition is given. Just we are going to consider two conditions. Let us, I am just taking the two conditions are, if I am taking n is equals to 1, okay. So I am just taking, if I am taking n is equals to 1, then what is that? A1 is equals to and A 2 to the power of 1 plus B minus 3 to the power of 1. So subsequently A1 is given as 8. So it is 2A and next minus 3B. Call this as given solution is 1 and this is 2 and this is 3. I am going to take it as 3. Then from this I can write A is equals to, then from these two equations I am going to simplify this. I am just taking, I am going to multiply this with 3 and going to add it. So it is 3A plus 3B is equals to minus 3. Just what I am doing, second equation, I multiplied with 3. So adding, so it is 5 is equals to 5A. So A is equals to 1 I am going to get. So if A is equals to 1, what about B is equals to? So it is minus 2. B equals to minus 2. Once if I am getting B is equals to minus 2, then substitute A and B values in equation 1. So from 1, what I am going to get? From 1, so I am going to get A n is equals to, A is equals to 1. So 2 to the power of n, B equals to minus 2, minus 2, minus 3 to the power of n. So this is the solution for the corresponding A naught and A8s. So like this we have to do this. Now go for the second problem. So here an is equals to, just we are going to given as an is equals to 3an minus 1 minus 2an minus 2. So now I am just taking it as, I am going to rewrite this. An is minus 3an minus 1 and next plus 2an minus 2 equals to 0. Now here what is the quotient of an? Quotient is Cn is equals to 1. Cn minus 1 is minus 3. Cn minus 2 is equals to 2. Now what we are going to take, the auxiliary equation is Cn k to the power of n or k square, Cn k square plus cn minus 1 k plus cn minus 2 equals to 0. So this is the auxiliary equation. Now I am going to substitute. This will become k square minus 3k plus 2 equals to 0. Equals to 0. So subsequently what I am going to get, k square minus 2k minus k plus 2 is 0. So k into k minus 2 minus 1 into k minus 2 is 0. So k minus 1 into k minus 2 is 0. So k equals to 1 comma 2. Once again we are going to get the real and distinct roots. So an is equals to a 1 to the power of n plus b 2 to the k 2 to the power of n. So this is the solution. Now if I am going to substitute, I am going to calculate what are a and b values. So n is equals to 0 if I am going to substitute. Then a naught is equals to a plus b. What is a naught is? This is implies a plus b is equals to 5. So call this as 1 and of course this as 2. Then I am going to take n is equals to 2. Okay, what is I am just taking? N is equals to 2. A2 is equals to, then it is a, then 2 to the power of 2. 2 to the power of 2 is equals to 4b plus 4b, which is implies a plus 4b is equals to a2 is 3. a2 is 3. So from this minus minus minus, so I am going to get a minus 3b is equals to 2. So b equals to minus 2 by 3. So I am just calculating. This is what I am going to get. This as a equals to, then b is b equals to, what I am going to get, it is right. So a plus b is equals to, then a2 is equals to 3. 2 to the power of is 4. It is 3. Okay. Then I am going to substitute a value here. A plus b. So a minus 2 by 3 is equals to 5. Call this as 3. Then I am going to calculate. This is a equals to 5 plus 2 by 3. So which is equals to 17 by 3. So just substitute this in here. So a is equals to 17 by 3 and 1 to the power of n, and b equals to minus 2 by 3 and 2 to the power of n. 2 to the power of n. Like this we can calculate. So now let us go for the other problem. So here also this is Cn is from this we are just calculating Cn is equals to 1. Cn minus 1 is equals to minus 6. Cn minus 2 is equals to 9. So what is that? Just it is a Cn k square. So it is k square minus Cn minus 1k, 6k and plus 9 equals to 0. So then it is a k minus 3 whole square is equals to 0. So what I am going to get, k equals to 3 comma 3. Repeated root. Real and repeated root. So the solution is an is equals to a plus bn. A plus bn and k 1 to the power of n. 3 to the power of n. 3 to the power of n. So that we are going to consider, and now this is the solution for this is just we have to consider it as let us I'm just taking this is the general solution. Now once again the same as usual method, just I am going to substitute n is equals to 0. Subsequently a naught is equals to a. N is equals to 0. Then directly I am going to get a. So a is equals to a naught is 5. So directly we are going to get a is equals to 5. Then n is equals to 1 if I substitute it. Then a1 is equals to a plus b and then it is 3. 3 power 1 is 1. Then it is a1 is equals to 12 is equals to a plus b and 3. So it is nothing but 3 4s. So I'm going to get a plus b is equals to 4 and b is equals to 4 minus a. It is nothing but 4 minus 5. So minus 1. So an is equals to a is equals to 5 I am getting, and b is equals to 1 minus 1 and then 3 power n. So this is the solution for this equation. The roots are real and repeated. Now let us go for the other problem. Then solve the recurrence relation. So this is the problem. Now here we are going to find out what is the equation can be written as an minus 2an minus 1 and plus 2an minus 2 is equals to 0. Now here Cn is equals to 1, Cn minus 1 is equals to minus 2, Cn minus 2 is equals to 2. Then the auxiliary equation is just we have to consider Cn k square minus plus Cn minus 1 k, so it is 2k plus 2 is equals to 0. Now this is minus b plus r minus, so the roots I am going to find out. So just 2 plus r minus b square minus 4ac by 2. So 2 plus r minus, then it is 2i by 2. So the roots are 1 plus r minus I. So the roots are complex roots we are getting. So whenever the roots are complex, then we are going to find the third case. So one is k1 is equals to 1 plus I and k2 is equals to 1 minus I. Now for this, if I am going to get like this, then we are going to find the solution. So for this, what is the solution is an is equals to r to the power of n, then it is a cos n theta plus b sin n theta. Then we have to find out what is the what is n and what is r. We have to calculate. So what about r is equals to? So here r is just I am going to calculate r is equals to modulus of k. What is k is equals to? This is the k. Then I am going to consider r k1. We can take it as modulus of k1 or modulus of k2, whatever it is, it will be. So it is a 1 plus square root of 1 plus 1. 1 plus 1 square. So it is nothing but a square root of 2. So this is r is this. And now theta is equals to tan inverse p q by p. Q is equals to 1 by 1. So which is a tan inverse of 1. This is equals to pi by 4. After getting theta and r values, these two are going to substitute in this expression. So now an is equals to root 2 to the power of n and then a cos n theta n pi by 4 plus b sin n pi by 4. So now this is, let us take this as equation 2. Now we are going to find out what are a and b values. So by substituting these conditions. So in this n is equals to 0 if I am taking, then a naught is equals to, this is whole power 0 is 1, a, n is equals to 0. N is equals to 0 is cos 0 is equals to 1 I am getting. and B sine 0 is 0. So what I am getting, A is equals to A naught. What about A naught is 1? So A is equals to 1. Now, if I am taking n is equals to 1, then A1 is equals to root 2 to the power of 1 and A cos pi by 4 plus B sin pi by 4. Then what about A1 is equals to 2? This is root 2 and A cos pi by 4. Cos pi by 4 is root 2. So it is nothing but root 2A and then this is root 2B. If I took root 2 as common, then what I am going to get 2 is equals to root 2 into root 2. So then it is A plus B. So now these are going to be simplified. Then I am going to get A plus B is equals to 1. I am going to get A plus B is equals to 1. Then if A is equals to sine pi by 4 is 1 by root 2. So I am just taking this as not this by root 2. By root 2. So then this I am going to write, these two are get cancelled. This will be 2. Then I am just taking it as 2. So now A value is equals to 1. So B is equals to 2 minus 1, which is 1. So A is equals to 1 and B is equals to 1. So after getting these values, then we are going to substitute in this expression in the equation 2. Then an is equals to root 2 to the power of n and A is 1 and B is 1. So cos n pi by 4 plus sin n pi by 4. So this is the solution for the given recurrence relation. So this is the solution for the given recurrence relation. So here in all the problems almost whenever the conditions are given, so we are going to find a particular solution. That means for those values, what are the values of A and B we are going to calculate. So for all the problems, this is the routine process. So we discussed so far the cases of the recurrence relation. Whenever the auxiliary equation will have a roots, those roots are, first problem, real and distinct. Those roots are real and distinct. Then how to find out the particular solution. Then the second problem, also real and distinct. So what is the solution? And the third problem, if it is a repeated roots. If it is a repeated root, that means k equal to 3 is repeated twice. Then what is the solution? And next, the fourth one is, if the roots are complex roots, then what is the solution? So this is in this session we have discussed only the second order linear homogeneous recurrence relation. The how we are going to get a solution for that. So in the next session we are going to discuss third order linear homogeneous recurrence relation. After that we are going to take the non-homogeneous second and higher order non-homogeneous recurrence relation. So with this I am going to conclude this session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.